Okay, I feel like it's been a long time, but we're back on track with the video lectures. Going to get caught up in the next couple of days. Today is a pretty easy one, very little calculus, and even at that, not too much trigonometry. So I hope you guys find this quick and easy and a little bit interesting. So the topic of the day is polar coordinates, and this is section 11.3 in the book. Now, traditionally, when we label a point, let's go to black, we would look at, we'd have a set of axes like this, and we'd say maybe there's a point here, and we'd label this point with x, y, like that. And say if this particular point were 5, 4, which seems reasonable. 1, 2, 3, 4, 5, and 1, 2, 3, 4. We could call that point 5, 4. And these are called Cartesian coordinates. And because this particular coordinate plane was developed or kind of formalized by René Descartes, who was the same guy that said, "I think, therefore I am," René Descartes, famous French mathematician slash philosopher. Well, that's not the only way we could find our way to that particular point. And so if I did it in a different color, I'm going to do these in green, I think. So that'll be a little weird, but I just want to keep polar coordinates and Cartesian coordinates separate. So if I put the same point here, and I said I could define this not only as an x and a y, but I could say this is some distance from the origin. I'm going to call this r, and then some angle down here, which traditionally we call theta. Okay, and there's a few important things to note about this. This is called the initial ray. So really it's not the x-axis, but it's in the same place as the x-axis. And that point right there is called the origin or the pole. And so what I would say is I would define this point, instead of x and y, I would define it by defining an r and a theta. And in this case, the r, well, if this is 5 and 4, and so I go back here and draw this in, we could use the Pythagorean Theorem and say a squared plus b squared equals c squared. So that's square root of, let's see, 41. So that comes out to be about, the radius here is 6.4, and the angle works out to be 38.7 degrees. So 6.4, 38.7. And the 6.4 again represents the distance from the origin, and the 38.7, and I'm going to put a little degrees there just to make sure that we know that's 38.7 degrees, represents the angle we have to go. Now, the analogy that I always use to kind of explain this, and this is a little childish, but I've always done it, so I'm going to keep doing it, is when I was growing up, I grew up in a small town, and we used to have parties off in a field somewhere. Really small town, and so we're surrounded by farms. Most of my friends were farmers, and say here we'd find this field, and we'd ride our bikes to the corner of the field. We'd park our bikes here. Well, whatever. That's a bicycle. And then say our party was going to be over here somewhere. We're going to have a little campfire and sing songs, play guitar, that type of stuff. So I could give directions in, 2 different ways. I could say walk east. I could say walk 5 minutes east, and then 4 minutes north. And so that would go, I'd go like this way for 5 minutes, and then I'd walk this way for 4 minutes. and I'd find all my friends reveling in the moonlight. Or the other option is I could tell someone to walk for 6.4 minutes at some angle, and in our case it'd be 38.7 degrees. 38.7 degrees. So either set of directions would get me to the same place. As far as the walking example goes, obviously it'd be faster to walk this way. 6.4 versus 9 minutes. But there's two ways to get there, okay? And that's the basic concept of polar coordinates. So let's make a few notes here. We know for sure that any point on the Cartesian plane can be represented with polar coordinates. Right, so if we do it in Cartesian here, and you're wondering why am I writing this so many times, but you'll see in a second, and then this is polar over here. All right. Well, my first point that I'm kind of using as an example is 5, 4, right? And we discovered that this could also be written as 6.4, comma 38.7 degrees, right? Well, what if I told someone, say I wanted to play a practical joke on them and they're dragging something heavy, I could tell them to walk backwards 6.4 minutes, and they have to face 218.7 degrees. Right? Does that make sense? So let's go back over to the left page here. So we're starting here where we parked the bicycle, and I'm going to say face that way, face the corner of the screen here, but then walk backwards. So that would be facing the wrong way, but then walking backwards. I could also tell them to write, or to walk 6.4 minutes forwards, but go down here and spin in one circle first. So they'd be pointed at 398.7 degrees. So what does this mean? And it kind of has important implications later on, is that Cartesian coordinates are unique. In other words, for this particular point in the plane here, there is one and only one set of Cartesian coordinates that would get me there. 5, 4 are the only ones that work. Whereas in polar coordinates are not. And we'll talk about that a little bit more in the next section. But basically that means if we have a polar graph, if we have a picture, a line, not all of the points on a particular line will fit the equation that made that line. So it becomes a little goofy there. So let's go to the next coordinate, or not. Are not unique. All right, I'm going to go to the next page and talk a little bit about converting between the two. Yeah, I'll do that on the next page. Okay, so converting between polar and Cartesian. All right, well, let's do a little trig review. Now this will be very elementary, but I know that some of you guys still struggle a little bit with your trig. So I will cover it begrudgingly. And let's do, we know that sine of theta equals opposite over hypotenuse. And I know that cosine of theta equals adjacent over hypotenuse, and the tangent of theta equals opposite over adjacent, right? So we remember that. So if I draw a picture here of kind of our classic right triangle, and I fill in, this is theta down here, and then this is the hypotenuse, and this is my opposite, and this is my adjacent. Well, I notice that hypotenuse, and say this is my point up here, so I make this P, and this is my origin down here, origin. So my opposite is actually the same as my y coordinate, and my adjacent is the same as my x coordinate. Now I think about the r, the radius, the distance I need to get from the origin to the point. This is my radius. The hypotenuse is the radius. All right, well, to get from polar to Cartesian, that doesn't work. I can't make my squiggly line very well that way. That x will equal, well, let's see, x is the adjacent side, so that's over here, so that's x over r. Well, the x would be r cosine theta, so x equals r times the cosine of theta, and then correspondingly y equals r sine of theta. All right, so that makes sense. All right, that's pretty easy. But if we look over to the other one over here, if we want to go Cartesian to polar, then this one is a little less obvious. We use the Pythagorean Theorem to say that x squared plus y squared equals r squared. So that one is okay. X squared plus y squared equals r squared. And then we can also use our trig, the tangent, because the opposite over adjacent is y over x. We can say that theta equals the arctangent, or the inverse tangent, get out of there, of y over x. All right, so let's do an example, and let's start with an easy example where we convert a polar point into a Cartesian point. And say I've got the polar point, or the polar coordinates, and that would be 4 and then pi over 6. And so remember, that is r theta. All right. Well, we know that x equals r cosine theta, so in this case it equals 4 times the cosine of pi over 6 is root 3 by 2. And so that equals 2 root 3. And then we know that y equals r sine of theta, which equals 4 times 1/2, which equals 2. So our point x, well, this leads us to the point xy, which is 2 root 3 comma, 2. All right, so that's going from polar coordinates to Cartesian coordinates. All right, a slightly more difficult example is to go the other way. And let's say I've got the Cartesian point and that would be -3 and root 3 like that. Well, the radius is easy because I know that r squared equals x squared plus y squared, which equals 12. And so that means r equals the square root of 12, which I know is 2 root 3. Okay, well, theta equals the arctan of y over x, which equals root 3 over negative 3, arctan of root 3 by 3, negative 3. All right, well, now we have to try to find some angle that has this tangent. The way to do this is to draw a picture. I know I'm negative 3 in the x direction and root 3 in this direction, so I draw a triangle in kind of standard position here. And this is actually theta over here, like that. And I know that the longer side here is going to be the negative 3, and the shorter side is going to be root 3. Why do I know that? Well, root 3 is smaller than 3. So what kind of angles have a root 3? And, well, those are the 30, 60, 90 type of triangles. So I'm going to say that the cosine of this one, of this angle, is going to be, I'm going to guess, root 3 by 2. And I'm going to guess that the sine is 1/2. And so that means the tangent of theta would be the sine over the cosine, which is 1/2 over root 3 by 2. And if I flip that around, that becomes 1 over root 3, which equals root 3 by 3. So that worked. Now, what angle has a sine of 1/2 and a cosine of root 3 by 2? Well, that would be, this is pi, this is, the origin, this is pi, so this is 5 pi over 6. Theta equals 5 pi over 6. So what did I do? I figured out the radius. That's the easy part. For theta, I figured out what y over x is, which is root 3 by 3. And then I guessed some angles that I know, and because I know that some of my usual angles have the cosine of root 3 by 2, and some of my usual angles have a sine of 1/2. I went through the algebra, and I figured out that that actually works out. This is supposed to be negative down here, and this is supposed to be negative, which makes that negative. If you were to punch this into your calculator, you'd get the wrong answer. Right? So you've got to think through. The x-coordinate has to be negative, the y-coordinate has to be positive for this particular case. So you've got to be really careful about doing that. Okay, let's keep charging ahead here and look at an equation, or a few equations in polar coordinates. So now we're looking at equations in polar coordinates. Well, what's an easy one? What if I said r equals 3? All right, what would that look like? Well, that would be just a circle with radius 3. Easy enough, right? Well, what if I said, I'm going to do this on the same one in a different color. If I said theta equals pi over 4, what would that be? Well, theta over equals pi over 4, it doesn't matter what r is, it's just going to be a ray going out this way. However, I could also go in the negative direction, and so that would give me a ray that goes out that way. So this one is theta equals pi over 4. All right, not especially interesting. I could do some inequalities, and let's do one that looks like this. Yeah, let's draw some coordinates here. I can say that I want to draw a picture of all the points where r is between 3 and 4. R is between 3 and 4. What would that look like? Well, that's just two circles, one with radius 3, and then a bigger one with radius 4. And my set of points that fit that are all these points in here. Right, so all of these fit in there. And then finally, I could do, I might as well do it over here since I will use this paper anyway. What if we have one that looks a little more interesting? Like I've got an equation that looks like this. R squared sine of 2 theta equals 2. Right, now if I were to draw a picture of this, boy, that'd be interesting. It's got some complex relationship between r, well, r squared actually, and then the sine of 2 theta. In these cases, we have to do a little manipulation, and with this particular one, I'm going to need to convert it to Cartesian coordinates first, because I'm more comfortable graphing it that way. So sine of 2 theta, I can split that up and write this as r squared times this part right here becomes 2 sine theta cosine theta. And that's a trig identity, many of which you've probably forgotten. So you might need to review some of these. Equals 2. Well, I can divide both sides by 2, so I'll get out the red pencil of cancellation here. The 2's cancel out. That's convenient for me. And I can rewrite this as r sine theta times r cosine theta equals 1. Well, r sine theta is y. R cosine theta is x, and that equals 1. So xy equals 1. I can rewrite that as y equals 1 over x. What does that one look like? That looks like this. It becomes a hyperbola around the origin. So most of these are just a little algebraic manipulation. None of them are terribly tricky, but I think you should be able to figure out most of the homework ones on your own. And I realize you don't have a ton of time at this point to get some homework done, but we'll get it done during class. Okay, I'll see you tomorrow.